Comparison of the efficiency of parallel algorithms KNN and NLM based on CUDA for large image processing. Problem statement. The purpose of this work is to conduct a comparative analysis of the effectiveness of the parallel algorithm KNN and NLM based on CUDA technology to accelerate the noise reduction of large-scale images obtained from the satellite. Statement of the research task: develop a parallel algorithm of KNN and NLM methods based on CUDA technology and implement them programmatically. Test and compare the noise reduction results for each algorithm, as well as compare both algorithms with each other. Measure the execution time of each algorithm with a different configuration of the computer system for further calculation of acceleration and comparative analysis of efficiency. Literature review. To date, many classic filtering algorithms have been proposed. Median, linear, and isotropic other classic filtering algorithms are usually capable of removing noise, but they have disadvantages because they lost a lot of information and affect the geometry of the images, which can give objects in the image completely different shape. One of the algorithms without the above disadvantages is non-local means. Because the principle is simple and the information contained in the image is better stored, NLM has become a popular algorithm for reducing noise. However, NLM has low runtime efficiency compared to traditional algorithms. Another effective algorithm in terms of reducing noise and keeping the original image informative is K-nearest neighbor. This algorithm is conceptually similar to above NLM, but as indicated in studies with lower computational complexity. Therefore, in theory, it should run faster than NLM. Parallel calculation. Both methods can be easily implemented using CUDA technology. Since this technology uses the simple parallel computing model, we don't need to parallelize the algorithms themselves. It is enough to implement a standard version of the algorithm in the form of a kernel function. The kernel function is actually a normal sequential program without organizing the launch of threads. Instead, the GPU runs many copies of given function in different streams. Consider in more detail the mechanism of organizing parallelized calculation. Host CPU performs a control role, runs tasks on the device, allocates memory on the device, moves memory. Device GPU performs the role subordinate, does only what the CPU tells him. Kernel task that the host runs on the device. Threads are grouped into blocks in the middle of which they have shared memory and run synchronously. The blocks are combined into grids, the main task of which is to serve as an isolated container to which the kernel function applies. Experiments and results. Research has been conducted on images of different dimensions and with different configurations of computing power to measure the operating time of algorithms with CPU-GPU comparison, where P is the number of pixels in the image and GPU is the number of streams per block. Table 1. NLM algorithm execution time in seconds with different CPU-GPU startup configuration. Table 2. KNN algorithm execution time in seconds with different CPU-GPU startup configuration. Discussions. The next step is to analyze our program execution time metrics and GPU acceleration factors. For clarity, tests were performed on different image sizes. From Table 1 and Table 2, we can see that the calculation on the CPU significantly exceeds the time spent on execution compared to the GPU. This is due to the high computational complexity of scale images. For tasks of this type, multiple threads on the CPU are not able to compete with thousands of graphics core threads. We can also observe that as the number of GPU threads increases, the time decreases significantly. In a more detailed analysis of the results, we can conclude that there is no clear favorite. Also, KNN shows better results with a small number of threads per block. The biggest time difference between CPU and GPU we get for scale images. This confirms the correctness of the choice of subject area of our task accelerating noise reduction. Conclusions. The result of each algorithm were analyzed, and it was found that both algorithms performed well in the task of reducing noise and restoring the original images obtained as the satellite images. To compare the results, tables were built for each algorithm with different program configurations. Regarding the obtained time metrics, we can conclude that parallel calculations using CUDA on GPUs are many times better than calculation on the CPU. It is for these algorithms that GPU and CUDA technology can achieve significant computational acceleration.